Okay, so let's think about these questions from last class. If I asked you to find the atomic mass of an element, someone raise your hand and tell me how we could go about doing that. And I don't want you to tell me that you look at the periodic table. Okay, how do I find the atomic mass? Yes, Isabel. Protons plus neutrons. Perfect. Okay, atomic mass is protons plus neutrons. And someone tell me where those are located in an atom. Yeah, Jake. In the nucleus. Very good. Protons and neutrons in the nucleus. Okay. Somebody raise your hand and tell me what the atomic number tells us. Yeah, Braden.
The number of protons.
Number of protons. Good. And the number of protons, is it specific for each element or does it vary per element? It's specific, right? A proton number or its atomic number gives an element its identity. Okay, it's very, very specific to each element. If I have an element with the atomic number of 4 and a charge of -2, someone tell me how many electrons it has. Yeah, Jenna, what do you think? 6. Perfect. Okay, someone explain that? Tell me why. Trevor, tell me why.
Okay, so there are 4 protons, and those would cancel out 4 electrons. And since it's a -2 charge, there has to be at least 2 electrons.
Perfect. Okay, in a neutral atom, the number of protons equals the number of electrons. So if this atom was neutral, we'd have 4 electrons to match our 4 protons. Since we know it has a charge of -2, we've got 2 extra electrons, which means we have 6. Okay, why don't we get the charge of -2 from taking away 2 protons? That would change the atomic number, right? That would change the atomic number and change the identity of the element, which is not what we want to do. Okay, so anytime the charge changes, it's because of a change of electrons, not because of a change of protons. All right. What's this type of atom called if we've got a charge on it? Yeah, Joe. An ion. Very good. And today we're going to extend this just a little bit, types of ions. So an anion, so this is new notes, you need to write this part down. An anion is any ion with a negative charge. An anion is any ion with a negative charge. Is that term familiar to you or is this new? This part's new. Okay. An anion is any ion with a negative charge. So anything that is a negatively charged particle is considered an anion. Okay, on the reverse side of that, a cation is anything with a positive charge. A cation has a positive charge. So the way that I like to remember this is for cation, it has a plus sign right in the word. Okay, cation is positive. Okay, it has a plus sign right in the word. Or if you like cats, they're positive. Okay, a cation has a positive charge. I don't like cats, so I don't think of it that way. Okay, but for those of you that like cats, you can think of it as cations having a positive charge. Get it? Their little paws. Do you get it? That's why I did this?
Yes.
Okay, all right. You guys are supposed to laugh at my corny jokes. Okay.
I was laughing.
All right, positive. Anions have an N in the word, so does cation, I know, but anions have negative charges, cations have positive charges. So there's a plus sign in the cation, or they are positive. Okay, so now on a test, when I see you go like this, I know that you're going to be thinking cations, positive. Okay? All right. That's my funny joke for the day. Okay, today we're going to talk about average atomic mass and how we calculate average atomic mass. Okay, and what it is, why we care about average atomic mass. So I want you to take a look at your periodic table of elements and take a look at atomic masses. Okay? If we know that the atomic mass is protons plus neutrons, why do so many atomic masses have decimal numbers? Right? You can't have half of a proton or half of a neutron, but yet all of our atomic masses go to decimal numbers. Okay? And the reason for that is because these atomic masses that are reported on your periodic table are average atomic masses. Okay? And they're averaged based on the availability or the abundance of each isotope of that element. Okay? Can someone remind me what an isotope is? Yeah, Trevor, what do you think?
Isn't that when it has more protons and neutrons?
Not necessarily. Nope, not necessarily. Miguel, what do you think?
Atoms of the same element with different mass.
Good. Atoms of the same element, so they've all got the same number of protons, but we've got differing number of neutrons. Okay, so different numbers of neutrons. So they're all the same mass, or they're all the same element, but they have different masses. So we looked at an example of hydrogen here, where it had 0 protons, where it had 0 neutrons, 1 neutron, and 2 neutrons. They had all different masses, but they had the same number of protons, which keeps its element identity. Okay, so the average atomic mass that's reported on those periodic tables is a weighted average, basically based on abundance of an element. So we're going to look at these different average atomic masses and see how to calculate these. Okay, so when we talk about elements, we talk about them as a relative abundance of their isotopes. Okay, and there's some elements that have very, very, very specific abundant isotopes, and some of them have lesser known isotopes. Okay. So this is kind of a review of what we just said. Isotopes are atoms of the same element with different masses. Okay, and remember, to change the mass of an element, you change the number of neutrons. You don't change the number of protons. That would change the element's identity. Okay, so average atomic mass takes into account how much of each isotope goes into a sample. So if I take 1,000 oxygen atoms, I might have 996 oxygen atoms with an atomic mass of 16. Okay? But those other remaining oxygen atoms might have an atomic mass of 18. Okay, so my average atomic mass of oxygen has to be an average of those two masses, a weighted average. Okay, and we're going to look at that here in just a second. Okay, it's going to be a weighted average. So we're going to look at the percentage of each isotope that's typically found in samples of our elements here. Okay, so if I would take 100 oxygen atoms, or 1,000, or 10,000, or 1,000,000, they're each going to have a typical relative abundance of each of those isotopes. Get the equation written down, and then I'll talk through what each of those means, okay? Okay, so this equation right here is telling us that the average atomic mass, an average atomic mass is what's reported to you on your periodic table. Okay, that is the average atomic mass. It's a weighted average of all isotopes of that element in their certain abundance. Okay, so what this is telling us is that if I have a percentage of our element A, I'm going to multiply that by its atomic mass. Okay, I'm going to add that to the percentage of abundant, or the isotope B. I'm going to add that to the percentage of isotope B times isotope B's mass. I'm going to do that for isotope C, and I could go on and on and on again. I could have 2 isotopes. I could have 10 isotopes of an element. It just depends on how many it's reported. Okay? Each element has a different number of isotopes, depending on its stability, depending on lots of different things. Okay? So it's usually between 2 to 4 isotopes that we'll see reported for each element that make up its average. Okay? But you can get upwards of 5 or 6. So let's try one here. If I look at the average atomic mass of copper, I'm telling you that there's 69.17% of the isotope that has an atomic mass of 62.929599. Okay? So every time I look at copper, there's 69.2% of it that has an atomic mass equal to this. Okay? The other 30.83% has an atomic mass of 64.92793. Okay? What's been done here to our percentages?
They've been turned into decimals.
Yep, we have to convert them to decimals. We don't multiply it by 69.17. We convert that to a decimal place. For you, I want to see if you can plug it into your calculator correctly. Okay, I've given you all the numbers. I've done most of the work for you. Go ahead and see if you can plug it in, and we're going to see if we match what's on the periodic table.
going or just stop at that?
Nope, just stop at about 2 decimal places. Okay? So does that that average atomic mass that you calculated, does it match what's on your periodic table for copper? You should have a periodic table in front of you. Copper has the atomic number of 29. Does it match?
Yes.
Okay, good. So the annotation maybe that would have come for this problem is we would have said we had, we would have said find the average atomic mass of an element that has a 69.17% of Cu, and then it has usually a hyphen, and then it gives you the atomic mass. 62.929599, and it tells you I have 30.83% Cu, 64.9277, whatever that number is, 93. Okay? So that's maybe what the problem would look like to begin with. You have to convert those percents into a decimal place, and then you'll plug it into that equation. Does that make sense? Okay, very good. So, yeah, Joe. Okay, so this time, how many isotopes do you have? 3 isotopes. So we do the same process, but we add all 3 of those together. $41.67. Do we agree? That's not quite what I had. Does 41 look like it's an average of those 3 numbers? No. Try it one more time. Try to plug it in one more time. Sarah, what'd you get? 33.25. 33.25. And what's our units here? AMU. Atomic mass unit. Okay, AMU. Okay. Did you get it fixed, Abby? Okay. Does this look like it's an average between those 3 numbers?
Yes. Yes.
Yes. And which is it closest to, our first, second, or our third isotope?
First.
Our first. Does that make sense because it's the most abundant?
Yeah, that makes so much sense.
Okay. It should be closer to that number because it's the most abundant. Yes. All right. So a molar mass is the mass of 1 mole of a pure substance. Okay, the mass of 1 mole of a pure substance. Okay, the mole is a unit of measure. Okay, so I want you to think of a mole as like a dozen. Okay, how many is a dozen baseballs? How many is a dozen donuts? How many is a dozen roses? There's 12 in a dozen, no matter what substance you're looking at. Okay? A mole acts as the same thing on a much bigger scale. Okay? So 1 mole of anything is equal to 6.022 times 10 to the 23rd molecules of that substance. Okay, so it's a much bigger version of a dozen. Okay? Anything that is considered to be 1 mole, we know it has 6.022 times 10 to the 23rd molecules of that substance in it. Okay? So we could have a mole of baseballs. Okay? We could have a mole of roses. It would be a lot, but we could do it. Okay? So it's 6.022 times 10 to the 23rd of anything is equal to 1 mole. Okay, so when we talk about molar mass, we're talking about what is the mass of 1 mole of this substance. If I take 6.02 times 10 to the 23rd of this substance, what's the mass of it? Okay, that's what the molar mass is. Grams per 1 mole. Okay, does that make sense? How many grams is in 1 mole of that substance? So the molar mass of an element is given to us on the periodic table, believe it or not. The molar mass is given to us on the periodic table. Okay, do you notice on your periodic table, look at the object's atomic mass. Does it have any units behind it? No. It doesn't have any units, right? It's just a number. Okay? So molar mass and average atomic mass, okay, or atomic mass, are the same value. They just have different units. Okay? So the molar mass and the atomic mass, or the average atomic mass of oxygen, are the same number. They have different units that go with them. Okay, so if I'm looking at the average atomic mass of oxygen, I know it's 15.99 AMU. But if I'm looking at the molar mass of oxygen, I know that 1 mole of oxygen atoms weighs 15.99 grams. Okay, so our units for molar mass are grams per mole, okay, or G/mol. Okay, so what this is telling us is that we have this many grams over 1 mole of our substance. Okay, so for oxygen, for example, 1 mole of oxygen weighs 16 grams, 15.999, which I'm rounding up to 16. Okay, are we clear on that? Don't let that part trip you up. In the same way, oxygen has an average atomic mass of 16 AMU. Okay, so do we understand that the numbers are the same? The units are just different depending on which we're looking at. Okay, average atomic mass is telling us the number of protons plus the number of neutrons. It's telling us mass on a singular atomic level. Okay, 1 single atom of oxygen has a mass of 16 AMU, but a mole of oxygen, okay, 6.02 times 10 to the 23rd atoms of oxygen, has a mass of 16 grams. Okay, so do we understand the difference between molar mass and average atomic mass?
Yes.
Yeah? Average atomic mass is 1 single atom. Molar mass is 1 mole of those atoms. Lots and lots and lots, and it's in grams per 1 mole. So our units are grams per mole. Okay? All right. So here, if we look at average atomic mass of carbon, it's 12.01 AMU. Tell me what our molar mass of carbon would be. 12.01 grams per mole. Perfect. Same number, just different units. Okay, so if we're looking at a mole of carbon and we put that mole of carbon on a balance, it would weigh 12.01 grams. Yes.
What's the sigma?
Okay, we can now determine molar mass of compounds. We can take molar mass a step farther besides elements. We can find molar mass of compounds. Okay, so we're going to be able to look at all of the elements within a compound, and we're going to be able to determine the mass of 1 mole of that substance, or its molar mass. So when we want to find the molar mass of a compound, we take into account every single atom in that compound. It's going to add to the mass of the overall compound. If we look at water, okay, the compound water, which is H2O. In that compound, we have 2 hydrogen atoms and we have 1 oxygen atom. Okay, so we're looking at molar mass here. We're going to find out what's the mass in grams of 1 mole of this substance. Okay, so we have 2 hydrogen atoms and 1 oxygen atoms. So we're going to find the molar mass of hydrogen. We know is 1.01 grams per mole. 1 single hydrogen atom has a molar mass of 1 gram per mole, but we have 2 hydrogen atoms. So we multiply that by 2 to work toward our overall compound here. Okay, so we're going to take 2 times 1.01 grams per mole, and that's going to give us 2.02 grams per mole for the molar mass of just the hydrogen within that compound. We're not done yet. We haven't looked at oxygen yet. Okay? If we look at our one oxygen atom, we're going to add that to it as well. Okay, so we're going to take the 2.02 grams per mole from hydrogen, and we're going to add that to our 16 grams per mole from our one oxygen atom, giving us a total molar mass of 18.02 grams per mole for water. Okay, so if I were going to look at 1 mole of water molecules, 6.022 times 10 to the 23rd molecules of water, it would have a mass of 18.02 grams. Okay, which indicates basically we need multiple of those single molecules within our compound. So when we're dealing with parentheses, for example, this molecule under here, which is called iron sulfate, we're going to take the number outside the parentheses and multiply it to everything inside those parentheses. Okay, so we're going to talk through how many of each atom we have in this particular molecule before we can calculate its molar mass. Okay, so our overall goal here is going to be to calculate molar mass of this iron sulfate molecule. But before we can do that, we need to determine how many of each atom, or how many of each element, we have in this molecule. Okay? So let's start with just the iron first. Does it have anything to do with the parentheses?
No.
The iron is outside the parentheses. So this 3 that's in regards to the parentheses does not have anything to do with the iron. Okay, we just care that there's how many iron atoms. Tell me how many iron atoms we have in this molecule. 2. We have 2 iron atoms, and iron is Fe. Sorry, in case you were unsure of that. This Fe right here is iron. Okay, so in this molecule we have 2 iron atoms. Okay, now's where it gets a little bit trickier. This 3 right here is distributed. Okay, we distribute the 3 to the sulfur, and we distribute the 3 to the oxygen. And when we use the distributive property, do we add those things or do we multiply them?
Multiply them.
We multiply. Okay, so tell me how many sulfur atoms I might have.
3.
I have 3 sulfur atoms. Good. Sulfur is the capital S. I have 3 sulfur atoms there. Okay, and what about our last oxygen? How many oxygen atoms do we have?
12.
We have 12. Because that 3 is distributed, it's multiplied by the 4, it's not added. Okay, it is distributed. Okay, so now let's go ahead and calculate molar mass. We know how many of each atom is in this molecule. We know the molar mass of each atom because it's given to us on the periodic table, and we're going to be able to multiply those as we want. Okay? So right here I've taken iron's average atomic mass. We have 2 of them, so I multiplied it by 2. I'm going to add that to sulfur's atomic mass, which we have 3 of, and I'm going to add that to oxygen's atomic mass, which we have 12 of. There's lots of different ways you can write this on your paper. You got to just kind of get into a rhythm that works well for you. I've seen people do it like this. Fe, we know has a 55.85. We know there's 2 of them, and then we would get that answer. We know sulfur is 32.07 times 3, and we know oxygen is 16 times 12. Okay, so go ahead and calculate these on your own. Yeah, Trevor, what do you think?
169.93
Okay, and what's our units?
grams G/mol.
Yep, grams per mole is how we say that. Grams per mole. Raise your hand if you agree. To the tenths place. Okay, if you're at the hundredths place, a little different. That's okay. Okay, but in general, yes, we agree. Yeah. Okay, good. How about the second one, magnesium chloride? Yeah, go ahead.
95.2 grams per mole.
95.2 grams per mole. Yes or no? Yeah, Caroline, what'd you have? 142.1 grams per mole. Raise your hand if you agree. Good. All right, very good. Okay, this is our last goal for today, is to get through percent composition. Yeah. So let me kind of just walk through briefly what percent composition means. Percent composition is going to tell us, out of a compound, what percent of that compound is made up of sodium molecules and what percent of that compound is made up of chloride atoms or chloride molecules. We're going to be able to break each compound down by its percent composition. So we're going to tell what each of these compounds is composed of percentage-wise. Okay, so we can find percent composition of elements in the compound, but we've got to find molar mass first. So that was why we solved for molar mass first. Now we can take it a step further and break each compound down based on its percent composition. Okay, so I might tell you that in water, every single water molecule is 11% hydrogen by mass. Okay, every single water molecule is made up of 11% hydrogen and 89% oxygen. That's what percent composition is telling us. Okay. So what we're going to do to find or to calculate percent composition is going to be, we're going to compare the mass of the entire compound to the mass of the specific element we're trying to find. Okay, compare the mass of the element to the mass of the entire compound. And these are working with molar mass. Okay, so with all these percent composition, we're going to work in molar mass, not AMU. Okay, so when we're finding percent composition, we still have to find molar mass of the whole compound, and then we're going to start looking at individual elements. Okay, so we're going to find the percent composition of sodium chloride, like I talked about. First thing that you need to do is find the molar mass of sodium chloride. Okay, and chloride is an element that we like to keep those 2 decimal places for. Okay, it's 35.45, so we want to keep it at 35.45. Don't round it up or down to a whole number. Okay, there's certain elements that we can round its molar mass to a whole number, like oxygen, like nitrogen, like sodium even. But chlorine is not one that we can round to a whole number. We got to keep those decimal places. Okay, so let's find the molar mass of sodium chloride. Okay, so I know the total molar mass is 58.45 of sodium chloride. I'm going to take the mass of sodium, the molar mass of sodium, which is 23, and I'm going to divide that by the total. Okay, so what you're going to do is you're basically going to take the element divided by the total molar mass. And that's going to give you the percent of that element. Okay, so 23 divided by 58.45 gives us 39.35%. Okay, really it gives us 0.3935, but we're going to convert that decimal back to a percent.